we're going to look at this rotational kinetic energy. If I have an irregularly shaped object, we can estimate its center of mass. Let's just say it's here, right? And there's going to be various particles of mass that are all at different distances around that object. And if this object starts to rotate about that center of mass, we're going to have all of those particles moving at a different rate. So we actually have to figure out what the kinetic energy is of every single particle. Now what's the same of every one of those particles is the angular velocity. Even though they're all different radii, the angular stays the same. It's rotating through the same number of radians in the same amount of time. So we're going to substitute in omega r into the v squared. Now the 1/2 is constant, the omega is constant, so we're going to pull those out of this sum, and we're left with the sum of all the mr squared. Now this is its own property, all right, and that's called the rotational inertia. Think about it as rotational mass. So I'm going to get rid of this object. So in our equation for kinetic energy, for the rotational values, we're left with 1/2 I gets replaced for this omega squared. And our linear is just still 1/2 the v squared. So we looked at how we would just replace the linear variable with the angular value, and anytime that we have mass, it gets replaced with I. And you can see that that's pretty much expected right there. So this is where we get a proof of how rotational inertia is replacing the mass, and it comes from this equation right here. Now we need to get some practice using that equation to figure out the rotational inertia of systems of particles as well as rigid bodies. So the next video we'll do systems of particles for rotational inertia.